In this video, we have some integrals we're going to evaluate using a U-substitution. Now, it doesn't have to be a U-substitution. You can use Z, you can use T, whatever you want. A lot of the formulas, general formulas you see, have the U, and that's where this probably comes from. Do you have to use a U-substitution to get the problem worked out? Not always. Sometimes it just makes it easier to set up the problem and solve it. It just facilitates the process. You use a chain rule when you use or take the derivative of a composite function. The U-substitution simply undoes the chain rule. So let's look at some of the basic formulas that you have. Basic integration formulas. The first one simply tells you that if you have the integral of a function f of u, u could be a function of x, k is a constant. Notice that's equal to k, integral of the function f of u, integral f of u with respect to u. In other words, you can bring the constant outside the integral. Now, if it's a variable, you can't do that. So you have formulas 1 and 2. Number 3 is 1. That's very popular. If you have the integral of e to the u du, that's always e to the u plus a constant. Now, if that's x, that comes out to e to the x plus c. Number 4, using the exponential. It's a standard exponential, a to the u. That's equal to, integral of that is 1 over ln of a times a, and the exponent is u. And here u generally will be a function of x. And then you have the ones involving some trig functions here. Integral of sine of u, with respect to u, is minus cosine. Integral of cosine is sine. Of course, you have your constant. And then you have some others there with secant squared, secant u, tangent u. Number 9 is very popular. If you have the integral of 1 over u du, or that could be written du over u. That's always equal to the natural log of absolute u plus your constant. Have some more integrals involving trig functions there. And these are the ones that you really should know. There's others, but these are just some, just giving you a sample of some of the ones you should know. And then I threw in one on number 14 there, involving the integral of an expression du over a squared plus a u squared, which leads to the arctangent or tangent inverse of the function u over a multiplied by 1 over a. So when you're doing something by integrating an expression, an integral, you want to see if you can set it up using a U-substitution. These are some of the formulas that you might want to use, and these are just some of them. And you can go through these, pause the video if you want. So let's go through the first one here. So we got the integral of 8 over 4x minus 5 dx. And I'm looking to write these in the form of some of those formulas that I just went over. So I'm going to let u, for this one, I'm going to let u equal to the denominator. That's a very typical approach when you're using the u substitution. So this will be a 4x minus 5. Then we take the derivative of both sides. So derivative of u on the right, on the left side rather, would be just du. And the right side, derivative of 4x minus 5. Derivative of 4x is 4. Derivative of constant minus 5 is 0. So this just gives me 4. And then this is dx. So notice, 4x minus 5, that's going to be my u. So now the object is to go ahead and transform this integral. But instead of an x variable, we want the u variable. So the 4x minus 5 will be replaced by u. X is not allowed once you make the substitution. The dx, I divide both sides by 4 here. This cancels out. This will be 4 over here. So I can rewrite this integral then as the integral of a is constant. Just leave it there. And then the dx is replaced by du over 4. End up with this. And then 4x minus 5 is replaced by u. So there's my substitution. Notice 4 and 8 are constant, so I can divide this 4 into 8. That's going to be 2. So this gives me then the integral of 2 over u du. Now remember, the constant you can always factor out of the integral. And I can run back and bring the constant out in front like this. And say this is going to be the integral of 1 over u du, or I can just make it du over u. And now this right here is one of the formulas we just looked at. And the formula told us that the integral of anything in this form is the natural log of absolute value of u, whatever u is. And then this is really the answer to this problem, except it's given in terms of u. You're always going to give the answer using the given variable, which was x. So let's just go back to the original variable. This will be 2 natural log of absolute value. Instead of u, then I just put in 4x minus 5. 4x minus 5 plus the constant of integration. Now, if you have something similar to this, you can do exactly the same thing. So in other words, let's suppose I change the problem and make this 4 into a 7. The derivative of 7x minus 5 is 7. So the only difference is this was really 8 over 4, which came out to 2. That were a 7, that would be 8 over 7. Everything else would be the same. If this were 9 instead of 4, exactly the same thing. This would be same thing, 8 over 9, and whatever this u came out to be here. Same thing. So you can't take shortcuts. Once you know what's happening when you use the U-substitution, you can take shortcuts. Unless your instructor tells you to show every single step using a U-substitution. So you have to be careful there. So remember, one of the formulas we looked at was that if you had the integral of e to the u du, that was always e to the u plus your constant of integration. Now, I point out that if you have a constant, say instead of just e to the u, say this were a 7, that would still be the same thing. You can take out the 7, and then the answer would just be this multiplied by 7. So this would be 7 e to the u plus a constant. So let's look at this way then. I'm going to let u equal to 3x to the third. Now notice, du is the derivative of 3x to the third. That would be 3 times 3 would be 9, x squared. And then you always have the dx over here. Think of it as du over dx, and you multiply by dx. So now, I want to rewrite this integral over here in terms of u instead of x. In other words, I want it to look like this one, right here. So let's see here. The integral then is going to equal to, so notice here I have a 9x squared dx. 9x squared dx is equal to du. So 9x squared right here, that product. I put those together, 9x squared dx, that's du. I'll put it on the right side, du. And then e, write it down. And then the exponent on this e is 3x cubed. But 3x cubed is your u. So we get that. Now we want the integral of this. We're using the formula. It's just e to the u plus c. So this is going to be e to the u plus c. But always go back to the original variable. This is the answer here in terms of u, but we started off with x. So then we just go over here and say, okay, e and u is 3x cubed plus the constant of integration. Now notice, if I take the derivative, and that's how you check these kind of problems. Take the derivative of the answer, and that's supposed to give you this integrand right here. Well, the derivative of constant is 0, so that cancels. The derivative of e to some power, in this case 3x cubed, is that same thing. So that's 3x to the third. Multiply, this is using the chain rule here, multiplying by 3x cubed, the derivative, that is, of 3x cubed, and that's 9x squared. See how the chain rule and the U-substitution relate to each other? Got 3x cubed, and the derivative of that is the 3, or the 9 rather, x squared. But anyway, for this one, the answer is e to the 3x cubed plus the constant of integration. So once you're working enough of these problems, you could probably figure out the answer without doing this, but sometimes you can see it better when you use the U-substitution. And I want to point out to you that had this been a 10 instead of a 9, this is still going to work out. It'll just involve a fraction, kind of like the first one. Now some can be a little bit tricky. If you look at number 3 here, you say, well, you know, what can I let u equal to? This one was pretty obvious because the derivative of this is this exactly. Had this been 7, the main thing is the variable. The x squared is still going to be there, so it still would have worked. You would have had a fraction for the answer there, but it still works. Now for this one here, number 3, we can let u equal to square root of x minus 1. That will probably work. Or I could let u equal to x minus 1. And I think I like that one better, even though the other one would also work. U equal to the square root of this would work. What you'd have to do is square both sides to eliminate the radical. So I'm going to leave it this way. And then this would be du. Taking the derivative of both sides. Derivative of x minus 1 is 1, but that's multiplied by the dx. So this is dx now. So now what do we need? For the x minus 1 here, that's going to be my u. Okay, my next step now is to convert this given integral into one involving the variable u instead of x. So x minus 1 will be the u. Notice here, dx and du, they're the same thing. They're equal. So that'll take care of that. The other thing I need now, okay, I can't have an x. But from this part right here, taking the 1 over there to the other side, adding 1 to both sides, I can say that x is equal to u plus 1. So let's go over here then. So this is going to be the integral. X now will be u plus 1. This will be u plus 1 here. And the x minus 1 is u. And that's the square root of that. I just split to the 1/2 power. And then dx is du. Now I have an integral involving only the variable u. If you have constants like a 7, that can always be factored. So you can still use that setup. So now it's just a very basic integration here. And multiply through by u to the 1/2. So u to the 1/2 times u here. This is a 1 here, so this will be u to the 3/2. And then 1 times u to the 1/2. Now this is just basic integration here. U to the 3/2 plus u to the 1/2 with respect to u. That's the integral. So we're going to just write this out as u. We integrate by adding 1 to the exponent. 3/2 and 1 will give me 5/2. And then we divide the coefficient 1 by that. I get 2/5. And the next one we have u. Add 1 to the 3/2. I get 3/2. Divide the 1 by in front of coefficient by 3/2. I get 2/3. And then I have the constant of integration. And that's pretty much it. The only thing we have to do now is go back to the original variable. So all we have to do now is just substitute the value of u, which is x minus 1. So this will be 2/5, and then the u here is going to be x minus 1. So I put x minus 1, the 5/2 plus, then 2/3 here, u to the 3/2, and u is x minus 1 to the 3/2 power, plus the constant of integration. So again, 2/5 here, and then x minus 1 to the 5/2 power, plus 2/3 here, and x minus 1 to the 3/2 power. And I can write this in terms of a radical here, but if there's no specific instructions given, you can leave it in this form. And that's the way I'm going to leave it here for this one here. So that's the solution for the third one. Now for the fourth one, you have the integral of 2x over 9 plus x squared. And you might think, well, this is going to involve partial fractions. But this is not going to factor, so it's not going to do much for you. But let me remind you of a formula that we looked at that had this form here. The integral of, you can say 1 over this here. I just leave it as du over a squared plus u squared. A is a constant, that's the number. U generally is going to be a function of x. This is going to equal to 1 over a, and this will be tangent inverse, or we can write it as arctangent of u over a, plus the constant of integration. So the task here then is to take this given integral. Can we write it in this form here? Can we make it look like this? You notice here we have a constant squared. You can look at this 9, and you can write that as 3 squared. So you can say, okay, if I relate this to this one over here, the 3 would be the a over here. But here I got u squared. So let's do this. Let's say, let's u equal to x squared. Because I can write x to the 4th can be written as x squared squared. So du would equal to derivative of 2x squared is 2x. This will be dx. So now let's look at this. This could be written. Now I'm going to try to write this in terms of u. I want it to look like this formula over here. So notice the product 2x dx, which is in the numerator, is also equal to du. So this will be du. Denominator is okay because I'll leave the 3 squared as 3 squared. And then remember the x squared is u, so this will be u squared. Now we're in business. This is now in this format where the 3 is the a, and of course u, of course, is the u. So this would be then, on the formula, this will be 1 over a. In our case, a is 3. So this will be 3 here. And then arctangent, I can also write this as tangent inverse of u over a. Okay? In our case, u is x squared over a. And in this example here, 3 plus the constant of integration. This is your solution to this one. Thanks for watching. We'll see you next time.